EV Expert E-Learning Diagnosis, EGMP, Module 12, DC Charging. Learning Objectives. 1. Explain the DC charging process. 2. Analyze the major data of DC charging sequence. Lesson 1. DC charging process. Let's look at the DC charging process. The VCMS recognizes the connection of the charging connector through the PD signal. It recognizes the type of the EVSE from 400-volt DC to 800-volt DC through the CP signal. Also, it requests the ICU to activate the IG3 relay to wake the charging-related controllers up. The BMS activates the pre-charge relay and the main relay negative to pre-charge the 800-volt capacitor. The multi-inverter activates the 400-volt relay and performs PWM control to pre-charge the neutral capacitor. After pre-charging the neutral capacitor of the multi-inverter, the BMS activates the main relay positive and deactivates the pre-charge relay. After that, the BMS activates the quick charger relay as requested by the VCMS. The VCMS requests the EVSE to charge through the PLC of the CP. The multi-inverter decides the charging method through the EVSE information received from the VCMS. Boost charging up to 800-volt DC takes place with 400-volt DC EVSE, and direct charging takes place with 800-volt DC EVSE. When the charging is completed or cancelled, the VCMS requests the BMS to deactivate the quick charger relay. The multi-inverter discharges the neutral capacitor and deactivates the 400-volt relay. The BMS deactivates the main relay to end the DC charging process. Lesson 2. DC charging sequence. Let's check the DC charging sequence in 19 steps. From steps 1 to 11 is the DC charging start sequence, and from steps 12 to 19 is the DC charging end sequence. Compared to AC charging, DC charging has a more complex sequence with more information, such as the control of the quick charger relay and the multi-inverter. As such information is exchanged via PLC, a good understanding on the key data will prove beneficial in diagnosis of issues related to DC charging. First, after fastening the charging connector to the EV, analyze the DC charging start sequence data. The PD voltage changes from 4.4 volts, and the charging connector engagement is detected. In the CCS2 type, the PD voltage changes to 3.7 volts when the charging connector is engaged. In the CCS1 type, the PD voltage changes to 1.5 volts when the charging connector is engaged. The CP voltage, previously 0.7 volt, changes to 9 volts when receiving power from the charger after the charging connector is fastened. The VCMS requests the ICU to control the IG3 relay on. The CP duty is then detected as 5%. The DC charging situation is recognized, and the EVSE prepares for charging. The MCU and BMS receive power from the IG3 circuit and prepare for charging while communicating with the VCMS. When the power line communication starts, the PLC logical network status changes to true, and the EVSE type is detected as DC extended. The VCMS receives data regarding the maximum charging voltage and current that the high voltage battery can accept from the BMS. The VCMS activates the EVSE S2 switch inside the VCMS, and the CP voltage changes from 9 volts to 6 volts. For 400-volt fast DC charging, the maximum voltage received by the VCMS through the PLC from the EVSE is indicated as 500 volts. For 800-volt ultra-fast DC charging, the EVSE maximum voltage is indicated as 825 volts. The VCMS controls the inlet lock actuator to lock the charging inlet. The inlet lock actuator senses the result and sends feedback to the VCMS. For safety, EVSE performs a charging cable isolation test before the charging begins. After the isolation test of the EVSE charging cable, the PCM cable check status changes from true to false. False means completion of the charging cable test. After that, the EVSE performs an internal isolation test. The capacitor of the EVSE and the neutral capacitor of EV's multi-inverter starts pre-charging to the same voltage before quick charger relay on. The purpose of this pre-charging is to match the voltage between the supply voltage of the EVSE and the neutral capacitor of the EV inverter before the charging starts. Accordingly, the surge current that may be generated at the start of charging is minimized to protect the high voltage circuit. The capacitor of the EVSE is being pre-charged, and the VCMS requests the BMS to activate the main relay to pre-charge the EV's neutral capacitor. Here, the quick charger relay is not activated yet. If both the quick charger relay positive and negative are welded, the voltage of the multi-inverter neutral capacitor rises in voltage of EVSE capacitor. By the request of the VCMS, the BMS activates the main relay of the high voltage battery, and the MCU activates the 400-volt relay of the multi-inverter. The MCU then performs PWM control and pre-charges the neutral capacitor of the inverter equal to the EVSE output voltage. For 400-volt fast DC charging, the EVSE's capacitor and the multi-inverter's neutral capacitor are pre-charged up to 450 volts. For 800-volt ultra-fast DC charging, the EVSE's capacitor and the multi-inverter's neutral capacitor are pre-charged up to the same voltage as the high-voltage battery. After pre-charging both the EVSE capacitor and the EV's neutral capacitor, the VCMS requests the BMS to activate the quick charger relay. The VCMS requests the EVSE to supply charging power with target voltage that the EV can handle. The EVSE starts the supply of the charging current depending on the request of the VCMS. The target current varies by the SOC of the high voltage battery. Until this step is the process on the DC charging start sequence. Next, let's analyze the DC charging end sequence data at the charging completion or cancellation situation. When the charging stop button of the EVSE is pressed, the EVSE transmits a charging stop signal to the VCMS through the PLC. At this point, the EVSE transfer power status will be indicated as false. The VCMS receives the charging end signal from the EVSE and then transmits the charging end command to the charging-related controllers, such as the MCU and the BMS. In addition, the EVSE target current from the VCMS changes to 0 amperes. The EVSE S2 switch inside the VCMS is turned off, and the CP voltage changes from 6 volts to 9 volts. the VCMS requests the BMS to deactivate the quick charger relay. The VCMS performs a welding check of the quick charger relay. Here, the EVSE discharges the internal capacitor. At this point, the quick charger relay is already turned off. If both the quick charger relay positive and negative are welded, the voltage of the multi-inverter neutral capacitor may flow to the EVSE in reverse, and there may be no drop in voltage. The VCMS requests the MCU to stop charging and to discharge the multi-inverter's neutral capacitor. By the request of the VCMS, the MCU discharges the inverter's neutral capacitor nearly to 0 volts. In addition, the VCMS requests the MCU to deactivate the 400-volt relay and the BMS to deactivate the main relay. After completing the neutral capacitor discharge at the multi-inverter, the MCU stops PWM control and deactivates the 400-volt relay. The VCMS then controls the inlet lock actuator to release the charging inlet lock. As the power line communication ends, the PLC logical network status is changed to false. Finally, when the charging connector is removed, the PD voltage becomes 4.4 volts and the CP voltage becomes 0.7 volts. Then, the DC charging end sequence is finished. Summary 1. DC charging process. The VCMS recognizes the charging condition through the PD and the CP signal. The BMS activates the PRA to pre-charge the 800-volt capacitor. The multi-inverter activates the 400-volt relay and performs PWM control to pre-charge the neutral capacitor. After that, the BMS activates the quick charger relay. Then, the high-voltage battery is charged by DC power with multi-inverter's PWM control. 2. DC charging sequence. When the charging connector is engaged, the PD voltage decreases from 4.4 volts. The CP voltage is powered by the charger and changes to 9 volts. The VCMS activates the EVSE S2 switch inside the VCMS, and the CP voltage changes to 6 volts. The BMS activates the main relay of the high-voltage battery, and the MCU activates the 400-volt relay of the multi-inverter. The MCU performs PWM control and pre-charges the neutral capacitor of the inverter equal to the EVSE output voltage. After that, the BMS activates the quick charger relay. Then, the EVSE starts power supply. When the charging stop button of the EVSE is pressed, the CP voltage changes to 9 volts, and the quick charger relay is deactivated with welding inspection. The EVSE discharges the internal capacitor, and the multi-inverter discharges the neutral capacitor. The MCU stops PWM control, deactivates the 400-volt relay, and the BMS deactivates the main relay.